Welcome back. Today we have Laurie, and she'll speak about the more practical aspects of specimen preparation.
Thank you, Shores. Okay, so you're all here because of the recent advances in the field that really allow us to achieve atomic resolution structures in cryo-EM. But it is still difficult to obtain these high-resolution structures for proteins. So why is this? Why do we not routinely achieve high-resolution structures in biology? This is an image of a platinum iridium specimen taken by Chris a few years ago on the Polara here at LMB. And clearly, the optics of the microscope aren't limiting. It's the specimens that are limiting us. And this is perhaps a typical example of what might happen in the lab. This is a purified protein. It looks protein complex. It looks clean on SDS page. It behaves well in solution. It might migrate on a nice symmetric peak on size exclusion chromatography, but when we put it on EM grids, it's aggregated and falling apart. This is a negative stain grid, but we often see the same or worse on cryo-EM. And this isn't an uncommon phenomenon. It happens because specimens are exposed to surfaces and conditions that are really different from inside the cell. There are 5 orders of magnitude more surface area to volume ratio in the thin films of buffer that we use in preparing cryo-EM grids than in a 1 microliter drop of water. But also many aspects of the specimen preparation are still poorly understood and difficult to master. So with the advent of direct electron detectors, easier to use microscopes, and better software, I think really one of the biggest challenges that we face is the reproducible preparation of high quality specimens. So in other words, going from our purified protein to these beautiful images that will yield a high resolution structure. And so to make cryo-EM more amenable to more specimens, we need to make specimen preparation more reproducible and more routine. And so the goal of my talk will be really to address some of the challenges we face in the practical aspects of specimen preparation. And I stole this slide from Chris Russo, who spoke earlier in the week, which just shows the limitations of electron beam instruments. And when I saw this, I thought this really kind of applied well to what we're talking about today, because many of these aspects are what we're trying to address when we prepare our specimens. So we want to stabilize them in the vacuum, make them as stable as possible to the electron beam, increase the contrast of our images as much as possible, and reduce the effects of charging if possible. So as Chris says here, the samples must be very thin and are quite fragile. They move around in the beam, and they're often difficult to make. So just as a kind of quick overview, what the goal of sample preparation is first to preserve the biological specimen in a native state such that it will give maximum contrast. And to obtain our high resolution structures, we want the best specimen possible. We want to use the optimal magnification, and Crystal spoke about that yesterday. We want to use a detector with the best DQE possible to obtain the best micrograph possibles. And then this will lead to the highest resolution structure with the least data. Now, we can often compensate for bad specimens by collecting more data, but we can all be more productive if we really optimize all aspects of specimen preparation and data collection. So specimen preparation, I think one of the biggest advances in the field that allowed us to do this was really the development of vitrification by Jacques Dubochet in the mid-1980s. And these are 2 really key papers in the field. If you haven't read them, I would suggest you find copies of them and have a read, because they're really great. He really elegantly explains how he was studying water and ways to make it vitreous, as in not a crystalline state. This is from the Quarterly Reviews in Biophysics paper, where Jacques Dubochet shows hexagonal ice, cubic ice, the crystalline forms, as well as vitreous ice, and discusses their properties, where they come from, and how to avoid them. These are some of the first images of a biological specimen in vitreous ice. This is the semeleaky forest virus, and it's really beautiful how you can see all the features of these viruses, and this is from 1984. Now, the methods that these grids were prepared are essentially unchanged. Richard showed a similar slide on Monday. And so this is one of the original vitrification manual plungers, and this is one that we use today at LMB. So there has been some new work in vitrification that I'll come back to at the end of my talk, but essentially the methods are essentially unchanged. The key thing is that the grid is plunged rapidly into liquid ethane at a high speed, so at over 1 meter per second. Now, Richard also showed this picture of the vitrobots where you have a controlled temperature and humidity chamber, and this does help make things more reproducible. And I think it makes it much easier to learn and for new users to make reproducible specimens. Now, the supports that we use have really been developed out of this method for vitrification. The sample is suspended in a thin film of vitreous ice in the vacuum of the microscope. And traditionally, we use these 3 millimeter metal mesh grids, which have over top a thin foil of holy substrate. So these holes are of order 1 micron in diameter. And the specimen is suspended across these holes and rapidly frozen, and that's what we image through these holes. Now, this needs to be thin, ideally just larger than the diameter of the protein to be imaged, and that minimizes inelastic and multiple scattering events and maximizes the contrast. So last year, Chris Russo and I wrote a review in Methods in Enzymology on really a systematic method for specimen preparation. And I think this is an efficient way of addressing the entire process, where each step of the process can be optimized. And if during evaluation any of these are not successful, we should go back. So perhaps I should show it a bit more like this. So at any stage, if it's not successful, we go back and prepare better protein. Okay, so I'm going to start here at the top, and I'm going to go through each of these steps. So protein preparation. Contaminating proteins or degradation products can really interfere with complex stability and subsequent computational analysis of the particle image. So before you even put your specimen on the cryo-EM grid, it's really important to evaluate the composition, the purity and homogeneity, the stability and the biochemical activity of the complex. So we use SDS page gels as well as native gels to evaluate the specimen. We use size exclusion chromatography. This would be an example of a protein that's probably not very suitable and should be optimized before imaging. Whereas something like this is size exclusion chromatography coupled to multi-angle light scattering, where you have a nice symmetric clear peak. This looks much better for cryo-EM. We can also use dynamic light scattering, for example, to evaluate the solution characteristics. But really, we want to optimize the buffer conditions at this stage. The salt, the pH, detergents, to optimize both the biochemical activity and the homogeneity and stability of the protein complex in solution. So again, just want to emphasize that all of these steps should be done prior to making the first EM specimen, since no reconstruction is going to be better than the preparation from which it was made. Another really important consideration is that the protein complex remains intact at the concentrations that we'll use for EM. So we don't use much, we use 2 to 4 microliters per grid, and the concentration can range from 50 nanomolar to 5 micromolar. So if you know the dissociation constant, or KD, for the subunits of the complex, you can calculate whether it's expected to remain intact at these concentrations that you would use to prepare your specimen. Experimentally, what we often do is take our protein and run it on size exclusion chromatography columns at decreasing concentrations to make sure that that complex is staying together at low concentrations. But what if your complex does dissociate at the concentrations required for cryo-EM. One possibility is to work at the concentrations above the KD and adjust the subsequent plasma and blotting conditions so that you can achieve a thin layer with only a monolayer of complex. You could optimize the buffer to increase the stability. Cross-linking has been used as well in the past to covalently link the sample together, possibly preventing dissociation after dilution. And I should point out that this also changes the surface properties of the particles, so it can change the orientation distribution on a grid. But importantly, you must minimize or remove aggregates due to intra-protein crosslinks that will inevitably occur. And one way to do this is using graphics, a method developed by Holger Stark's lab, but we've successfully used size exclusion chromatography to remove the aggregates. Okay. After suitable protein is purified, the next step is really to evaluate it using negative stain. And this is really fast and really easy. And what you're looking for is these discrete particles. These are ribosomes on a negative stain grid. You want discrete particles. You want to evaluate the stability of the protein complex and look at the size and shape of those particles. So in negative stain, the sample is embedded in a layer of heavy metal salts. We often use uranyl acetate or uranyl formate. And this surrounds the protein like a shell. So when you image a negative stain specimen, you're really imaging the solvent-excluded surface and the shape of the protein molecule. And negative staining was developed a long time ago. This paper is from 1959. And the reason that it works is shown here. And this plot shows the cross-sections for elastic and inelastic scattering as a function of energy. And the cross-section is really an effective area that quantifies the likelihood of a scattering event when the incident beam strikes the target object. And so for metals, the cross-section for elastic scattering is higher than the cross-section for inelastic scattering. And this is what makes negative stain so good. Carbon, by comparison, is down here. So here's an example. This is a few years old from David Barford's lab. This is the anaphase promoting complex, where there's evaluation of this sample by STS Page, by chromatography. And here are some beautiful negative stain images with discrete individual particles. So this really shows that it's homogeneous. And just to remind you, it's the denser part of the specimens cause more scattering, and that's why the stain is scattering here. The protein appears white, whereas in cryo, the protein appears black. So for negative staining, there's really excellent contrast, even with a modest dose on our inexpensive Spirit microscopes. So as Richard said on Monday, this is really quick. We can make negative stain grids almost as fast as and evaluate them as fast as we can run a gel and look at the proteins on a gel. But it gives you so much information. We can screen many different conditions in a day. It has very high contrast, even for small molecules. It's only mildly radiation sensitive and relatively straightforward and easy to learn. Disadvantages of negative stain are, of course, it has limited resolution. And sometimes proteins can be damaged or distorted. But in our experience, if a sample looks really good in negative stain, it's much more likely to behave well in cryo. So once we're convinced that we have a homogeneous sample using negative stain and biophysical methods, we move to cryo-EM. And to begin with, we're looking for stability of the protein in the ice, the particle size and shape to evaluate those and make sure they're consistent with what we expect, and the particle distribution versus concentration. So in cryo-EM, the sample is rapidly frozen in a buffer such that the the water molecules have no time to crystallize. So it's very fast, on the order of 10 to the -4 seconds. And it preserves the proteins in a hydrated, near-native-like environment. The contrast is low, so we need to minimize the background signal. We do that by making it as thin as possible. But also, water is a poor conductor, so the sample must be thin, less than a couple microns, Otherwise, the thermal conductivity of the water itself will prevent the water from cooling fast enough to be vitreous. Now, at 4 degrees Celsius and 90% relative humidity, the evaporation of that thin film is of the order of 100 angstroms per second. So if you blot your grid and wait 2 seconds before plunging, a 400 angstrom film can be concentrated by a factor of 2. So it's really important to work as fast as possible once the specimen is on the grid to prevent those effects of evaporation, to work at 100% humidity and 4 degrees C. It's also important to work fast to minimize the interaction that the protein has with the air-water interface. And I'll come back to that a little bit later. Now, it's important that the ethane is at the right temperature, and Chris developed a cryostat to keep the ethane cold enough that it freezes quickly, but not so cold that it's solid. And these are available in the EM prep room for you to use. And the details are published last year. Okay, so the supports themselves. Now, these are specified in units of lines per inch. That's what the mesh is. So we usually use grids of mesh 200 to 400 lines per inch. And the squares on these grids are between 60 and 130 microns across. Across the grid, as I've already said, is suspended a foil which has holes in it. We usually use these quantifoil style holes, which have a regular repeating array. But in the past, people have used both lacy carbon and holy carbon. Now, carbon has been used traditionally because it's relatively electron transparent, and it's really straightforward to manufacture into foils. But I'll tell you a little bit more about the new foils that we've been using. And again, the sample is suspended across these holes. So, some practical advice on how to handle these. First of all, we always check these, or we advise that you check these in an optical microscope before you use them. And what you want to look for is pieces of lint or dirt or bits of plastic that are left over on the grid. And you want to check that they're flat. Because if they're not flat, as you plunge it, it'll bend and break the foil. It's also really important to handle the grids at the rim. So this is the tweezers. They should be holding just the rim. Crystal showed a nice image yesterday of a grid that's been damaged by tweezers. And this is the kind of thing that happens. So although that grid had some good data on it, you can see that actually the integrity of the foil is really compromised if you don't handle the grids properly. And I think this can really degrade the performance of the grids. You see how far this damage extends. We recommend storing the grids in glass dishes and handling them in a way that minimizes contamination and static charges, so preferably without a glove, with a wrist grounding strap, and using glass dishes to avoid the grids flying away because of static charge like this. The support surfaces are often hydrophobic when you get them, and this prevents the efficient spreading of aqueous solutions on the grids. So to control the hydrophilicity, we treat them with low-energy plasmas. And these plasmas are created by ionization of a low-pressure gas. If we do it in air, we call it glow discharging, but there are also plasma chambers that use defined mixtures of gases, including oxygen, argon, and hydrogen. So the ions interact with the surface to remove contamination and to render it hydrophilic. These are the plasmas generated in some of the glow discharging apparatuses here at LMB. And these are all done in residual air. All of these are effective in increasing the hydrophilicity of the support surfaces, but have varying degrees of reproducibility. And if you don't do it properly, they can damage the supports. So as you can see, these plasmas are often non-uniform, and this can vary the exposure dose quite significantly, even within one batch. We have a Fischioni plasma chamber here. There's also one made by Ethane. And again, these provide a more defined mixture, a more reproducible way to render your grids hydrophilic. There's also a custom holder for this Fischioni plasma chamber in the EM prep room that you can put up to 10 grids in for treatment. So this image shows what happens when you plasma treat your grids. There's a 3 microliter drop of water applied to a grid before and after plasma treatment. And you can see the decrease in contact angle here, which demonstrates the improved wetting after plasma treatment. Okay, so once you've made your grids and you've put them in a microscope, you want to evaluate the ice thickness and uniformity, the phase of the ice, and the protein concentration and stability. And this can often be done on the Spirit or an entry-level microscope, because all of these things you can see on that microscope. If you have a small protein, you may want to use the F20. So Christos covered this yesterday, so I won't spend much time on it. But the important thing is really to evaluate your ice quality. Is it vitreous? Is it free of contamination? And if you have crystalline ice, some of the possible sources could be during plunge freezing, ice crystals from your liquid nitrogen, and warm-up of the grid during handling. As I've mentioned, the contrast of proteins in vitreous ice is low, so it's important to ensure that the ice is only slightly thicker than the protein particle that you're imaging to maximize the contrast. So a water layer that's too thin will exclude proteins, and this is apparent from this ring of excluded proteins here. But if you have a grid like this, it's likely that adjacent holes may have slightly thicker ice that could be used for imaging. Another problem you may encounter is incomplete wetting, and here your grid is probably not hydrophilic enough, so you should adjust your plasma conditions to achieve more uniform spreading of the water on the grid. Okay, so this is the ice on the grid. What about the proteins within the ice? The proteins are exposed to many surfaces when we make cryo-EM grids, and this can really affect the way they're distributed in the ice. And so the surfaces they're exposed to include the air-water interface, amorphous carbon, the metal support structures, and filter paper. And I think this tomogram of ribosomes in ice taken by Tonmei illustrates that nicely. So here's the amorphous carbon layer. This is the bulk ice. And then the top of the ice layer is here where you see this contamination. And what I hope you can see is that almost all of the ribosomes are sitting on the amorphous carbon layer. There's a few of them at the air-water interface, and there's almost no ribosomes in the bulk ice layer in the middle. And so it's really the surfaces, both the carbon and the air-water interface, that affect the protein distribution. This can lead to an overall lack of reproducibility from grid to grid. Now, often the protein concentration, because of these surface effects, does not match the protein concentration in solution. So the protein density can be higher than expected if the particles tend to adsorb to the surface, and lower than expected if they repel the surface or tend to adsorb to the support structures themselves. So checking whether these match the solution in concentration and the solution on your grid can really inform strategies for sample preparation. And Vinod and Richard wrote a review last year in which they have this table which really gives for a given concentration of protein, the number of particles that you should expect in the thin layer of vitreous ice. So for example, for a 1 megadalton protein complex in 800 angstrom thick ice, you would expect 100 particles per micron squared if it's at 2 mg per mil. But a 250 kilodalton protein under the same conditions should have 400 proteins per micron squared. So we often don't see the same number of proteins on the grids as we would expect to see from the concentration in solution. So what should you do if this happens? So if it's stable in solution, I would suggest looking at the following parameters. First, buffer optimizations. If you change the charge of your protein, does it change where it's distributed in the ice? You could add small amounts of detergents or lipids to protect the protein from the air-water interface. You can change your blotting and plasma conditions. Is the ice too thick or is it too thin? Or you could use an extra continuous supporting layer, and this provides another surface for the proteins to adsorb to. And you saw this in the tomogram. The ribosomes stuck to the amorphous carbon layer. And this is relatively straightforward to use in the lab. We make amorphous carbon films. We can float them down on top of the EM grids. But the problem with amorphous carbon film is that it contributes substantial background signal. So it might be okay if you're studying ribosomes, but not so good if you have a 150 kilodalton protein. So in that case, you would like to use a thinner support layer, for example, graphene. And graphene is an ideal support layer to use because it's a one atom thick hexagonal lattice of carbon atoms with extremely good conductivity properties and mechanical strength. It's also effectively invisible at the resolutions we use in electron microscopy. But the problem is that pristine graphene is hydrophobic, and so you must use some other way to render it hydrophilic and allow wetting of the surface. This is some ribosomes that were applied to pristine graphene, and you can see that there's kind of puddles of denatured protein that's totally unsuitable for imaging. So a number of methods have been developed to overcome this. One of them is using graphene oxide. This is an image of the separase securin complex from Andy Boland and Thomas Martin in the lab. And graphene oxide has been gaining in popularity because it's straightforward to use and deposit on grids. However, reproducibility and coverage is difficult, and it still contributes some background signal. Graphene supports, on the other hand, are difficult to make, but would have more ideal properties. And so here we used partial hydrogenation of the graphene surface to show that ribosomes with the same solution concentration, different hydrogen plasma treatments affect how many ribosomes adsorb to that surface. So with no graphene, there's very few ribosomes, and they're mostly stuck to the edges of the hole. With a 20-second hydrogen plasma treatment of graphene, there are a good distribution of ribosomes, and with increasing plasma treatments, there are more ribosomes. So you can control the adsorption of particles to graphene independent of the solution concentration of ribosomes. So this may be particularly useful for small proteins where the background noise in the image is more detrimental. Okay, so we use diagnostic cryo-EM to evaluate the specimen. And once we've done that, once we're sure that the particle's stable, it has the right size and shape, and the distribution is correct versus the concentration, we want to move on to an initial cryo-EM data collection. And the goal here is really to obtain 2D reference-free class averages with high resolution features, so at the level of secondary structure. We can also obtain an initial 3D model and evaluate the orientation, distribution, and particle yield. So at this point, it's important to mention that the quality of our images at this stage are really important. And you've already heard during the course about radiation-induced motion. And this happens because when we image the specimen with the electron beam, bonds are broken both within the grid structure itself as well as within the ice. And this causes charges to accumulate and exerts forces on the sample such that the ice in the hole can bend and distort. So new direct electron detectors have really allowed us to measure exactly how the specimen behaves in the beam. And we were studying graphene at about the same time as the new detectors were available. So we started looking at particle movement. And what we found was that on average, the particles on graphene were moving less than the particles on, these are ribosomes, on amorphous carbon. And so to quantify this, we made these speed plots. And these are plots of the root mean square displacement, the RMS displacement of an ensemble of thousands of ribosomes on many grids plotted versus the fluence. And so the slope of these curves is the speed, so we call them speed plots. And what you can see here for ribosomes mounted on amorphous carbon films, there's a large variation in speeds. There's 3 different grids here. And this is probably due to the poor reproducibility of making those carbon films. So you can also see that we measure 2 phases of motion here, an initial faster phase and a second slower phase. So on average, these ribosomes on carbon are moving around 5 angstroms over that exposure, which is 16 electrons per angstrom squared. Now we can then use this metric to compare the movement of ribosomes on different support structures and see how they perform. So if we don't use that extra layer of amorphous carbon, the movement of ribosomes is a bit more reproducible, but there's still quite a lot of movement, especially at the initiation of irradiation here. But on graphene, the movement is less and it's more reproducible. So these experiments really showed us at the time that the support structure could strongly influence the behavior of the specimen in the beam. And so we developed a new type of support called ultrafoils, where both the metal grid and this Holy support foil on top are made out of a single material, gold. And they look like this. Here's the array of micron-sized holes in the grid, but now instead of amorphous carbon here, we have a polycrystalline metal. So the reason that we did this, got rid of the carbon, was this. And if you take a bare carbon grid and mount it in the electron microscope in cryo conditions and tilt it to 30 degrees, you can image the entire hole. And if you track the edge of this hole, you see that it's moving a lot. It's actually moving, in this case, by over 200 angstroms in the Z direction. So in the direction that's perpendicular to the plane of the image. And now we don't normally notice this vertical movement in single particle work because it's perpendicular to the plane of the image. But if we compare that movement to the movement of the gold grids, you can see that the difference is very striking. These gold grids are not moving at all. So putting these 2 side by side, you can see just how big the difference is. And we, again, quantified this motion by measuring the movement on many different grids. And on average, the movement of the gold grids is 50 times less than the movement of the traditional carbon-based grids. So again, this is in the Z direction. If we instead look at the ribosomes moving in the XY plane in the image, we can plot that using these speed plots. Again, the RMS displacement of an ensemble of ribosomes versus the fluence. And when we compare those to gold, you can see that the motion is reduced significantly, such that now, in a typical exposure, there's around 2 angstroms of movement, RMS displacement, across that exposure, compared to 4 to 5. So there's a 2-fold reduction in the movement of the XY plane, and movement in the XY plane on these new gold grids. So we published how to make these and also commercialize these, and it's led to a number of groups using them. So here are some examples of high-resolution structures published in the last year, and all of these were done independently of us. Actually, Amédée Desgeorges pointed out in his paper that he switched to using gold grids, and by doing that, he could collect much less data and get the same resolution structures. So he was able to determine more structures of this ryanodine receptor in more states because he was collecting less data. So why do these grids work? I'll just briefly go through this. One reason is due to thermal contraction. So when you cool a traditional grid to liquid nitrogen temperature, the metal shrinks more than the carbon. And this causes a wrinkling of the film and a loss of tension. Whereas if the entire grid structure is made out of the same material, it shrinks uniformly, and the flexural rigidity of the foil is maintained after cryoplunging. So this is one factor that reduces movement of the support. Buildup of charge on the foil is likely a major force, and so we measured the conductivity of these thin films, and you can see that the conductivity of the thin gold films is around 5 orders of magnitude more conductive than the thin carbon films. And so this conductivity will help reduce accumulation of charges on the support. And finally, these gold grids probably work because as you irradiate the gold, it generates secondary electrons next to the suspended ice. And this prevents accumulation of charges in the ice. Okay, so some practical considerations. If you use gold grids, how do you focus without carbon? We talked about focusing yesterday with Christos. But when you put these gold grids in the microscope, they look different because they're made of a polycrystalline metal. And this metal is about 500 angstroms thick, so you can still see through it. But because it's a polycrystalline metal and not an amorphous material, there's no longer tone rings to use for focusing. But it turns out that this isn't a problem. This is a focus series that Chris took of the edge of a gold hole. And what you can see is that if you look at the Fresnel fringes here at the edge of the hole, so you can still see the Fresnel fringes as you pass through, move from under to over focus. And you can also see these bright spots that extend into the hole. And these are delocalized lattice fringes from the individual crystals of gold in the gold foil. And they move further away from the edge the further you are from focus. And so if you look at a static montage of those images here, at the top is the edge of the hole. And it shows that actually it's quite easy to focus, either using the fringes or using those bright spots. Another way to focus is to minimize the image shift when the beam is tilted, and that's shown on the bottom montage. And this is the method that's used by automated data collection procedures. And again, it works very well on gold because there's so much contrast in these images. So how should you set up the electron beam? And this applies to any grid, really. The easiest way to set up the beam is to set up a symmetric illumination where you illuminate the entire hole and all the way around the edges. And so we tested the movement of particles within these holes with different illumination conditions. So if you have a symmetric illumination condition, if it's slightly asymmetric, or if you're not illuminating the entire hole. And so what we found when we looked at particle motion is that the particles move in the normal way in the first two conditions, but as soon as the beam no longer covers the entire hole, the particles begin to move and the image quality degrades. So we recommend symmetrically illuminating the entire hole with a small region of gold or carbon all the way around, and not collecting multiple images per hole. And this will give you the best images possible. This is just to remind me to say that it's still possible to, if you need to have a thin layer of amorphous carbon, you can put those on top of gold grids. And we found that it doesn't degrade the performance of the gold supports. Okay, so now you have high resolution 2D classes, and you do an initial 3D reconstruction. One problem you might encounter is preferred orientation. And so this is something that you should evaluate early on. This is a reconstruction of ADS ribosomes, and there's a severe problem here with with preferred orientations. And so Katerina has been working in Chris Russo's lab to develop a metric to evaluate this from a small number of particles. So in other words, which is better? These are 4 different ribosome data sets which have clearly different orientation distributions, but just by looking at them, it's hard to tell which one would be better. And so Chris and Katerina developed a metric using point spread functions to describe how good a particular orientation distribution is. And here they are ranked in order. And so it's not necessarily obvious just by looking at these which one would be better. So methods like this will really allow you to optimize specimen preparation and get the most out of your data collection. This shows also how if you were to improve the orientation distribution, for example, going from this green curve to this green curve, you could improve the resolution of your reconstruction. You could also improve the resolution, of course, if you were here by collecting more particles. But it's important to realize that if your data quality aren't very good, so here if you have a high B factor, collecting more data isn't going to help you very much. So evaluating the improvement in resolution with increasing number of particles is really important. And improving your images will probably get you there much faster than just increasing the number of particles. Okay, so we're almost to the end. We now have high-resolution 2D classes where you can see secondary structure. You have an initial model that looks okay. Your orientation distribution looks okay. Now it's time to collect a high-resolution data set. Again, I think it's important here to get the best data possible so that you can get the highest resolution structure from the least amount of data and with the least effort. Now, many of these aspects that you would evaluate will be discussed next week, including validation of the model, angular accuracy, the local and overall resolution, and how to separate out different conformational states. I just wanted to mention one thing here, which is motion statistics, because this relates to the specimen. And so we can use motion core, motion tracking software, to detect problems with the specimen, with the microscope, and with the beam alignments. So here we've plotted the motion core statistics for particles on carbon on gold grids. And you can see that there's a really different distribution of the particle, of the motion on the two supports. But you can also use this to evaluate your specimens and make sure that they're stable in the beam and optimal. So this can really be used as a diagnostic tool for both specimen and imaging quality. Okay, so looking forward, we really want to move from this trial and error process of trying many different things and testing them in the microscope to a much more controlled and reproducible method. And ideally, the support will ensure that the specimen moves less than the resolution of the microscope that's used to image it. The support will inhibit the buildup of charge that may distort the images. And the support will help control the orientation and distribution of proteins within the ice. So in the future, we really need to address better vitrification methods, and there are a number of groups working on new freezing methods. There are several prototypes available, so hopefully within the near future, these will be on the market, and there'll be new ways to freeze proteins. In particular, to get the protein, to freeze the protein faster after you've put it on the grid and perhaps minimize that contact with the air-water interface. There's also been some developments in new time-resolved processes, so hopefully we'll be able to look at more time-resolved aspects. Rapid screening methods will be helped by more affordable, easier-to-use screening microscopes that Richard and Christos mentioned. Reducing the radiation-induced motion and charging further will also improve our images. And new surface modifications will allow tunable interactions with surfaces. And so together, I think this will really allow us to reach the theoretical limit of EM in a more reproducible way. And we can collect less data. We'll have to get the same resolution structure, we'll have less time on the microscope and less image processing. Jake's smiling. Less data with better images and better specimens. And so just to finish, I'd like to thank the entire EM community here at LMB and you for your attention.